Well, good afternoon, everybody, and welcome to our live event, Women in Particle Physics. I'm Rachael Padman. I'm an astrophysicist, and I'm just about to retire as Director of Studies in Physics at Newnham. My predecessor but one was Janet Carter, who went on to become head of the High Energy Physics Group in the Cavendish Laboratory. And I'm really thrilled we've been able to elect two young particle physicists to fellowships in the last few years. Tina Potter, who is taking over from me next year, is a reader in physics at the Cavendish and has a particular interest in trying to work out what the so-called dark matter might be, which is a subject close to my heart as an astrophysicist. Maria Ubiali is the Sheila Edmonds Lecturer in Mathematics at Newnham and works in the Department of Applied Maths and Theoretical Physics. She works on the structure of the proton. Today, they're going to share their experiences as researchers in the field. They'll talk for about 25 to 30 minutes, which leaves us time at the end for questions. So if you do have any questions, then please click on the Q&A button on your screen and type them in. So without further ado, let me ask Tina to start the session.
Hello, everybody. It's my pleasure to speak to you about myself and also something close to my heart, my research today. So if we could have the next slide, please. Thank you. So I'll start off by who I am so that you can have put everything in context here. So I started off in a place which was very different to Cambridge. I was raised in Croydon and absolutely loved physics and maths at school, and so went on to study it quite naturally at university at Royal Holloway, University of London, which is where I was first exposed to particle physics, or high energy physics. It's got quite a few names. And I stayed there to do my PhD and do research in the experiment that I'm about to present to you today. After that, I went down to the University of Sussex to start a new experimental group down there for my postdoc, which was where life started to completely change, where we got our first dog, which you can see my wonderful dogs there, and then our second dog a couple of years later, and we were joined by our first child, Freddie, in 2014 as well, which was a very, very big lifestyle change. And then after I came back from maternity leave, a job came up at Cambridge, an early careers lectureship, which I applied for and got, and then came all the way up here to Cambridge to begin my lectureship. And again, life changed when we had our second child as well, little Emmy there. And then when I came back from that maternity leave, I managed to secure a permanent lectureship here at Cambridge, which has been absolutely wonderful. So I've been here since 2015, and with Newnham as well since 2015, which was an incredibly welcoming experience. They welcomed me with open arms, and I've settled in very quickly. And I hope to be with them, of course, for the rest of the time. And I'd like to continue, of course, at Cambridge. I don't know quite what's in mind for the future in terms of family and who I am, though, of course, I'm hoping certainly for more dogs. I say 2021, they were almost finished, but maybe 2022 for some more dogs. But okay, let's next move on to the research now. So if I could have the next slide, please. I would like to tell you what high energy physics is. So very, very short and simple, it's the study of the fundamental particles in the universe and the forces that govern their interactions. So we actually have so as far as we know, a finite number of unique particles that make up our universe. So we're talking about the smallest, most fundamental building blocks of our universe. There are 12 particles called fermions, and they are on the outside of this ring here. You may have heard of some of them, for example, the electron, but there's heavier versions called the muon and the tau. And there's three very ghostly particles called neutrinos, which caused a little bit of a stir a few years ago. And then we've got 6 further ones called quarks. These all have fantastic names, by the way: up, charm, top, down, strange, and bottom. So these 12 particles are the ones that make up, actually just 3 of them really, make up the mass of our universe that we know today. All of the other ones are unstable, were kicking around in high energy interactions and back in the early universe, but have decayed down to a couple of the stable ones now. Now, in high energy physics, we have 3 fundamental forces. Gravity is completely missing from this set of theories, but we have 3 fundamental forces that we can describe. The first is the electromagnetic force, which you might be very familiar with, which is governed by the photon. So the photon itself is a fundamental particle in our model. And then we have the strong force, the gluon, which glues our quarks together to form things like protons and neutrons that are inside the center of atoms. And then we have W and Z bosons, which are responsible for things like radioactive decay. And the newest kid on the block here at the center of these circles is the Higgs boson, which is responsible for mass generation. So we think we have this very simple, very straightforward set of theories to really describe all of these particles and their interactions. And it seems really straightforward, but is it really? So I'd like to tell you next, if we could go to the next slide, please, why we like to study high energy physics. So this slide maybe not showing up too well on the broadcast, but we'll see. So we are sort of about 13 point something billion years into the universe here, sort of far right of this picture here. But if we go back to the very, very early stages of the universe, to the Big Bang itself, we're trying to understand what kind of physics led us from the Big Bang to where we are today. And we understand things to a certain degree, back to a certain point. But of course, the universe is not visibly accessible to us back at those times. Our telescopes cannot see the universe back just a few seconds after the Big Bang. So what we like to do is build our own time machines to try and see this physics, to understand what was going on there. We build experiments that create very high energy collisions to try and recreate the conditions that were present a few seconds after the Big Bang and understand the physics that was going on there that led us to where we are now. So if we could go to the next slide, please. There are some big questions that we're trying to answer in high energy physics, in particle physics. One of them is, what are we made of? So when we have a look out at the universe, we can see stars, planets, gas. We understand what that's made of. That's made of our fundamental particles that I just showed you. But there's also a lot of evidence that actually says the universe, that's only a tiny, tiny, tiny part of the content of our universe. There's something called dark matter that makes up the bulk of our universe, and something even more mysterious called dark energy that makes up the rest. And we really don't understand the nature of that matter and that energy. So we've got a picture here on the top right of two clusters of galaxies colliding, taken through two different kinds of lenses. The first is the sort of pink matter that you can see there, and that's taken using X-ray telescopes, and you can see the luminous matter, the matter that we can really see with the X-rays. And as these two clusters of galaxies have moved through each other, the matter as we know it has sort of slowed down, interacted with each other, and it's shooting out these nice hot X-rays. But the interesting part is actually the blue part, and that picture is taken using gravitational lensing. And this is the non-standard matter in the cluster of galaxies you can think of. It's passed through, not interacting, not slowing down at all, passed through almost like a ghost, and it's sort of ahead of the rest of the matter that's interacted. And this is one of the many smoke signals of dark matter in our universe. So what are we even made of? What is the universe made of? We actually don't have a clue what most of it is made of. We'd like to understand how we even got here. There is some small difference between matter and antimatter that meant that the rest of the universe, when it was created, did not just annihilate back down to nothing. We're trying to understand why this new particle, the Higgs mass, is actually quite as low in mass as it is, and why it isn't off at the highest energy scales of the universe. And we'd also, another big question is, we'd like to try and understand gravity in the context of these fundamental particles and forces. At the moment, all of our theories about particles governing them, the sort of being the messengers of these forces, doesn't work with gravity. And of course, that's the force that we're most familiar with. So we would really like to incorporate gravity one day. So some really big questions. What are we made of? How did we get here? And how do we incorporate everything under one umbrella? So if we go to the next slide, please. So I'd like to say a little bit more about dark matter because I find it absolutely fascinating. So for many, many decades now, we've been studying the way that galaxies rotate out there in the universe, and they actually rotate far faster than we can actually account for the mass that we can see. So when we look at the galaxies, we can see the stars, we know how much luminous matter there is, but they're rotating far too quickly. A bit like if you were on the roundabout, a roundabout and going far too quickly, you would get flung off of the roundabout. The matter in these galaxies should literally get flung out of these galaxies because they're moving so fast. They're not, they are being held together. There is far more gravitational force holding these in than we would expect from the matter that we can see. So galaxies, there's actually this dark matter that we cannot visibly see that is holding the galaxies together and allowing them to rotate this quickly. We can also have a look at the cosmic microwave background. If everybody remembers old CRT televisions, it's that static that you see on your television there. That is actually the cosmic microwave background radiation, a very ghostly ancient light from the very early universe. And we can go and measure that and measure small differences that we see in that light across very large angles in the universe. And it's telling us lots of different things. When we have a look at something called the power spectrum of this light, it's telling us that actually only about 5% of our universe is matter that we know about 26% of it is this dark matter, and about 69% of the universe is something called dark energy, which I have no idea about at the moment. That's definitely more Rachel's area than me. So as far as we know, there are no candidates for this dark matter in all of our fundamental particles. They're either not stable, the ones we know about, or they're charged. They don't fit the bill. We know that it's got to be really stable and very neutral and weakly interacting. So if we go to the next slide, I'll try and explain what I'm doing to try and find out the nature of this dark matter. So there's a few things that you can do to look for dark matter. There's three main different ways, but one way that I'm doing is I'm trying to take our standard model, our known particles, in this case protons, ramp them up to really high energies, smash them together and try and make some of this dark matter in the lab. So I'm using the Large Hadron Collider, which is a massive accelerator just outside of Geneva in Switzerland, or it crosses Switzerland and the French borders actually. We are ramping up these protons to the highest energy collisions that we've ever done before in this 27-kilometer ring underground. We ramp up these protons that we're taking basically from a bottle of hydrogen gas to very, very high energies, smashing them together and hoping to create these dark matter particles. You can see a picture of the tunnel in this middle picture here. It is an absolutely fabulous machine down there. And around this ring, we've built 4 different experiments to try and discover new and interesting things. So if you go to the next slide, please. So the Large Hadron Collider, I cannot stress how much this is a fantastic, and I think one of mankind's actually greatest achievements. It is, historically, it's the largest experiment that we've ever built, and also the one with the most people collaborating together, really coming together. We've got particle physicists, engineers, accelerator scientists, theorists, all coming together to make this experiment work. So you can see a picture here of the kind of layout that we've got just outside of Geneva. The ring on top, you cannot see the accelerator ring from the ground. It's actually underground. But around this point, we've got, around this ring, we've built 4 different experiments, which are specialized, very, very specialized, massive detectors built to try and detect new phenomena or new particles that we're interested in. So we take these protons and we accelerate them around this massive, massive 27-kilometer complex, bring them together to collide at each one of these 4 points, and these massive detectors try and unpick what happened in these collisions, trying to find these new fundamental particles or new explanations for things like dark matter. And it's a fantastic collaboration, all of these people coming together to share the beam time, share the data, and really share the knowledge, and also share the technology with the rest of the world as well. So if we could go to the next slide, please. The Large Hadron Collider is a massive, I mean, physically very massive experiment, and also trying to answer some very big questions, but it's also doing this on a very long time scale. So we turned on the Large Hadron Collider in 2011. And in 2012, we managed to discover the Higgs boson, and I know Emerita is going to talk a little bit more about that. And we're over here now in 2021. We've been running for almost 10 years now. We've only taken, where are we at? We've only taken about 5% of the data that we're going to take on the lifetime of the experiment. We're going to make some upgrades to the Large Hadron Collider and continue running out to sort of the late 2030s before we really do complete this experiment. So we're only about halfway through the lifetime of our experiment. We're hoping to find some fantastic new things. So at this point, I'm going to hand over to Maria, who's going to tell you a little more about her work and how it fits in with the Large Hadron Collider.
Thank you very much, Tina. If we can go back to the presentation, I start with a couple of slides from my side. So first of all, let me tell you who am I. So I was raised in Italy, in Milan, and I studied there theoretical particle physics. And then I went to Edinburgh to do my PhD, partially there and partially in Belgium, in Louvain. And then I went to Germany to do my first postdoc in Aachen. And that is where I had my first child, the one you can see on the right side of the picture, Anna. And then in 2013, I moved to Cambridge for my second postdoc at the Cavendish Laboratory. And that is where the brunette in the middle, Veronica, was born. And in 2016, I started to have my group, so following my ideas as a PI, thanks to the Israel Society Dorothy Hodgkin Fellowship. And in 2017, I moved to the maths department with the lectureship. And at the same time, I joined Newnham. That for me was the same experience as for Tina, a wonderful, welcoming college that really make me feel so empowered and, in an environment that sometimes is not very easy. And when I started my lectureship, I had my third child. And very recently, I started a new exciting research as a PI for an ERC starting grant. So I have a group of postdocs and PhD students who I work together with, and we are trying to answer new fascinating questions that we put together in the past couple of years. So we just started, and it's the beginning of a fascinating journey, hopefully. So if I can go to the next slide. Yes, let me show you for 1 minute this video that brings you down into the tunnel in Geneva, this Large Hadron Collider that Tina has already introduced really powerfully. So if you can start the video, I show you that's a simulation of what actually happens there. So you can see that the protons, which are these two beams, are extracted from a source of protons, and they're accelerated into larger and larger rings thanks to powerful magnet technologies. And when they reach almost the speed of light, they go into the big tunnel, this 27 kilometers long tunnel underneath Geneva. And as you can see here, so they travel into this tunnel, which is close to the absolute zero in terms of temperature, so that they can go free. And as you can see in a second, the protons are not actually elementary particles because they are made of the quarks that Tina was talking about before. And look at what happens now. When they smash in the middle of the detector over there, out of two tiny particles, you see a huge amount of other particles. So each of these lines that you see is a new particle that is created as a result of the lot of energy that was there in each of the proton beams that is so big that it can create mass. So you can really see the relativity at work. You can really see Einstein's special relativity, E equal to mc squared. So the energy transforms into mass. So out of one proton, you have 300 things, 300 stuff coming out of there. So if we can go to the next slide, I tell you a bit more of what is my job, because I work with Tina as a theorist, not as an experimentalist. And what I do in my daily research is we use maths, so we use powerful mathematical tools in order to provide theoretical predictions for what we expect to happen. So this is a picture that these detectors, this big camera, take every second. And as theorists, we give our numbers to tell, that's what we expect to happen based on the model that we know everything about. But actually, our hope is that we find deviations from our expectations. So we hope to be proven wrong by the experiment, because we hope to find something new on top of what we already know. So we really think, okay, so what if instead of the particles that Tina was listing before, we have a new X particles? That would be extremely exciting, because it would open up a new window into our universe and will show us that what we know is incomplete. So it will open the door to something unknown, which is what we are really hoping for. So if we go to the next slide. Part of what I do is fascinating, because in order to provide, to make these theoretical predictions, to give numbers to the experimentalists, we really need to know really well how is the proton made in terms of quarks and these gluons, so the particle that glue them together, because you might have studied in school that you have 2 up quark and 1 down quark, but actually protons are much more exciting than that. There is a lot of life inside the proton, because there is continuously quark, anti-quark, matter, antimatter forming inside the proton. So in order to understand what's going to happen, so which one of the quarks or the gluon is going to collide with the other guy when we had this collision, we really need to characterize the proton really well. And something that I'm doing with my group is something a bit interdisciplinary, because we use the idea of artificial intelligence, so reproducing neural network, the neuronal connection that are in our brain into this artificial neural network. And these are very powerful tools that allows us to understand how the protons are made. So that's something that I find really fascinating, how we can always learn from other disciplines and apply things that belong to biology into our field and get a lot out of it. And then if we can go to the next slide, I would really like just to conclude and give you a bit of what Tina and I and many other particle physics live. So we are really excited, because the kind of picture that I was showing you before is just one of the billions of pictures we can take every second. So there is a huge amount of data taking, and this is going to go on for 20 more years. So with so many data to analyze, we can really expect to have surprising discoveries to be just around the corner. And I think that, I don't know if you can read it. It's a sentence by Richard Feynman that I like very much, that basically says that, let me have a look at it, that the same thrill, the same awe and mystery come again and again when you look at any problem deeply enough. With more knowledge comes deeper, more wonderful mystery, luring one on to penetrate deeper still, never concerned that the answer may find disappointing, but with pleasure and confidence we turn each new stone to find unimagined strangeness, leading on to more wonderful questions and mystery. Certainly a grand adventure. So that's how I feel, and I'm sure Tina feels too. And that's why we wanted to share with you our experience of particle physicists.
Right, well, thank you very much both. Thank you, Tina. Thank you, Maria, for that great insight into what you do. And I think you've done a masterful job in putting it into language that we can all hope to understand part of. And thank you, Maria, particularly for that quote from Richard Feynman, who's one of my heroes. And I think he just has a wonderful way with words and expressing the mysteries of what we do. I haven't got any questions in the chat yet. I'm sure there will be some, but while they're coming, let me just ask, Maria, you sort of alluded to the fact that it hasn't always been easy. And I think that's not just juggling children. But physics as a whole is a very male-dominated subject, and I'm just wondering if either of you would like to make comment on how the experience has been for you, given that sort of overwhelming majority of men. What's the field like? Is it welcoming, not welcoming?
It can be, no, I think it can be hard at times, but it's definitely worth, because most of the people that I encountered in the field are people who have this passion that we share. So people who really care for knowing the truth and sharing things, sharing data, sharing knowledge in order to advance in the field and grow in the personal adventure of finding something unknown. So this is what most people are. Of course, you often find yourself with big egos, and that's something that, as a woman, sometimes is difficult to deal with, because it's really male-dominated, especially in my field of theories. So I think it's very important to have a big networking, and a place like Newnham, or places in which you really feel that your confidence builds up, because there is no need of having a big ego to succeed in particle physics. I think I've met many people with great heart and great humility who do their job and do amazing discoveries, and they contribute to the whole community. So I really think you need a network, a place that teaches you to just be yourself and be happy and keep going on your path, because that's what gives you the biggest satisfaction.
Right, thank you. I see Tina nodding there, so I'll sort of take that, because we now do have some questions in the chat. So one from Helen, who asks whether we will ever understand what dark matter or quantum physics means, what it means philosophically, apart from the maths. I don't know who'd like to have a go at that.
I love that question. No, it's a really important point. I think we can do a lot more work, particularly in quantum physics, to understand it a little bit more philosophically. It's a fantastic mathematical tool right now, but the sort of level of depth of understanding there, I think, is yet to come. But dark matter, I would say, if it is a fundamental particle of the universe, it is something, if we can make it, if we can study it with the experiments that we have right now, it is something that I think we should get a really good understanding of, just like the Higgs boson. We have a very good understanding of it now, but I think it will open up more doors and more questions that we'll want to go on to study, just like the Higgs has.
Right. Now the questions are coming in, and one, let me just bounce it to somebody different. So Maria, question, don't know who it's from. Do our own bodies contain dark matter?
That's a very interesting question. It might be, so dark matter is special because it's something that does not interact in any visible way with the other particles that we know. So for example, we call it dark because it doesn't interact electromagnetically, so we do not see it shine, we do not see anything that has to do with light, which is electromagnetic radiation. So we might as well have a lot of dark matter going through us at the moment without knowing that, because it doesn't interact with anything that we have in our body. So I don't know if Tina has a better answer as an experimentalist, but
exactly, there is a WIMP wind going through us right now. We think that our galaxy, there's dark matter inside the Milky Way, and as our solar system travels through the Milky Way, we are traveling through a dark matter wind, we think. So yes, it should be passing through you absolutely unknowingly right now.
A wonderful little poem by John Updike about neutrinos, but I won't try and reproduce it here, but people might want to look it up afterwards. More questions here. Interesting one for another anonymous one, picking up on what Maria said about the beauty of maths in her video, and how the mathematician's also an artist. Is that also the same for Tina? Actually, it says it's also the same for Rachel and Tina, but I think this is your talk. So, Tina, over to you.
Oh, I'm an experimentalist, so it's a little less elegant and a little messier. Yes, it's very much trying different things, and we do sometimes come up with the most beautiful and elegant solutions for things, but there's a lot of mess and it's a less artful way of getting there, certainly.
The next one looks pretty imperious in a way. It's from Principal Rose. I think I know who that is. It says, I love Maria's quote that you hope to be proved wrong, meaning to find something new, which sounds like a very positive approach to failure. Is it easy to keep that positive approach? How do you stay positive?
Yeah, that's a very good question. So I think that at least for me, you always somehow, in my experience as a researcher, you always hope to discover something you don't know yet. And very often, the way in which you discover that is even accepting the failure, that you might have an idea, you might have an explanation for a phenomenon, you build your beautiful maths, you build your beautiful computer program in order to simulate that, and it doesn't work. So you can say, fine, and be discouraged, or you can say, wow, it means that there is something more than what I understand at the moment. So what can this tell me? And then you go to the next step in a dialogue with other researchers, with your students. There is always something coming out of it, which can be great. For example, one of the main areas of my research came out of a failure, because I went to Leuven as a PhD student trying to answer a question, and I failed in answering the question because I was doing calculation and they simply didn't work. And this made me reconnect with my master thesis supervisor at CERN while I was very discouraged. And then talking to this person, we actually had an idea that completely, that was the opposite of what I was starting from. And that idea actually worked. And so we opened a new line of research. We started to collaborate. We involved 2 more people who were at CERN at the same time. So I really think that in my experience, very often the fact that you fail because your original idea is wrong can open some fascinating paths that you haven't thought about.
Okay, thank you, Maria. Lots more questions here now. Question for Tina. Why is the Hadron Collider underground? How long did it take to build, and what are the upgrades going to be?
Well, it's underground because it would take up a lot of surface land otherwise. So it's literally put away, one where we can shield any radiation that comes out of it. The surrounding bedrock is a fantastic absorber of anything that could cause problems. Yes, and it doesn't take up all the land on top that's used, for example, that people are sometimes living in their houses and farming on, or even industrial places. How long did it take to build? I think from the start, well, the tunnel was already there. For starters, the tunnel was a reused tunnel from the Large Electron Positron Collider that was out at CERN. So we reused that 27-kilometer tunnel, which is a very good reuse. And then I think when we took out that accelerator and put in the new one, plus digging out new caverns for new experiments and building thens, well, I think from start to finish, we're talking about at least 15 years. No, maybe a little bit less than that, 10 years from the building. But we're talking about probably another decade before that, where there was all the planning and the technical design and the finalization of plans there, and also the R&D push. So these things are very much, they can take decades to plan and build, and they're very long-term experiments as well, decades to run as well, and also probably another decade before we fully finish analyzing the data that come out from it.
And the question about upgrades, what is the main point of the upgrade then?
There's lots of upgrades. The main big upgrade that's probably worth pointing out is the upgrade to the high luminosity Large Hadron Collider that's going to happen after the next run of data that we take. And this is going to upgrade our accelerator to collide the protons at the same energy, but to collide them at faster rates so that we can take more and more collisions at faster rates. And it'll give us data at faster rates, around, if I remember correctly, around 10 times faster. So we'll be taking data very, very, very quickly and hopefully be able to take a large enough data set to spot the very rare, very interesting processes. I hope by that point we would have discovered something like dark matter or some kind of new phenomena that we're searching for, and we'll be using this data to characterize it. But it's very likely that we might be looking for something very, very rare, and we'll need that large data set. So we'll be taking it, we'll be smashing them together at faster rates. So
there's just a wonderful set of questions here, and I'm sure we're not going to get through them all. So sorry to people who are putting them in we don't get to answer. But the next one I thought, I like, speaking to the woman part of women and particle physics, how has it been balancing a cutting-edge research career with bringing up a family? And would you have any tips for aspiring researchers also facing this challenge?
I can say a few words. It's definitely challenging, but possible. So it's I think it's really accepting the fact that you have to change a bit the way you work, and that you can't, life is full of things that you cannot foresee, because every time maybe you have a big conference and one of the child gets sick and you have to adapt to that. But it's also a big source of joy. So for me, it's a source of mess for sure, but at the same time, a source of joy that keeps giving me motivation. And it's very exciting to see your kids asking you, but mommy, why do you have to go, again to that conference? You explain, that there is something that is beautiful, that is worth working for and spending your energies for. And you do it also for them, to show that you can succeed because you have a passion and it's worth pursuing it. So I think there is not just the minus side of course, having to readapt or sometimes being too tired after a night of not sleep. That's not the end of the world. On the positive side, there is the amazing motivation that they give you, because they keep fueling your natural curiosity, and you're showing young people that you have around that there is something really beautiful, and that whatever they want to do in life, they can do it,
It certainly it's given me perspective as well. I mean, having children is, there's a lot of daunting things and things that you believed were out of your reach, and then you do this and they're suddenly not so hard. So the perspective that has come with having a family has been, I think, very, very good for me, and I've really seen what I'm capable of, and I can push harder as well. So I think it's part of a very important balance to life and life experience.
We have quite a lot of really quite philosophical questions here, but I hope you don't mind if I keep feeding them to you. But anonymous one here. We sometimes hear people distinguish between arts and science, yet Tina and Maria are both talking about physics and maths being beautiful, elegant, and artful. Would they like to comment on the aesthetics of physics, and also comment on some people's tendency to make a dichotomy between art and science?
If I can start, perhaps. No, I've always been fascinated by art, but I didn't have any artistic skills, so that was a big frustration. And that's how physics came into my horizon, because somehow, even when you just study physics at the undergraduate level, you see how, for example, Maxwell's equation, you can write them in a super elegant way, and this can explain the magnetic and electric phenomena that we see around us. And it's always a source of joy and surprise to see how such a small equation can make you understand such a big variety of phenomena. So I think there is always somehow the parallel I see. So there are two parallels I see. So first of all, the idea of elegance and simplicity. So we always go back to this idea to try to make sense of complex phenomena, to try to simplify them and understand them more in depth. And when we do that step of unifying things that seem to be completely different, we make a leap in our understanding of nature. And then the second thing that at least I see from my point of view is that reality is there. So there is something in nature that you try to describe, and you go on this adventure to try to understand the laws of nature, but they're already there. So it's like being a sculptor, and you try to really take away all the rocks around the figure that is there, and you want that figure to come out. So in a sense, it's something that you are in front of a reality that you have not made, but you try to discover in its simplicity and beauty. And to do that, you have to work hard and remove everything that is unnecessary, a bit like a sculpture.
What a lovely analogy. Tina, do you have anything more to add to that?
I don't think I could put that any better. I love that analogy, Maria. I'm going to squirrel that one away.
Well, here's a bit of a change. So I have a question from Beth, which says, you've both mentioned the Big Bang Theory, and in the comedy program, The Big Bang Theory, there is constant discussion about string theory and dark matter. Please, could you explain what Sheldon is working on and what he's doing?
Yeah. Well, there is an idea that our fundamental particles are actually, or can be described by vibrating strings, and the way they vibrate and the modes that they vibrate at gives them their physical properties that we see in the universe today. And it comes with lots of additional spatial dimensions and really cool things, and things like dark matter drop out of this very naturally as well. Unfortunately, the problem with string theory is that it is yet to give us an experimentally verifiable prediction that tells us that string theory is absolutely correct. So at the moment, it's a very, very nice way of mathematically describing the universe, but we do not know if it's the correct way of describing it. But it's very much separate to dark matter. Dark matter drops out of it quite naturally. It might be that string theory or something similar or on the way up to it is our sort of final theory of everything, but as yet we're not there.
Right. I don't know whether that will help Beth, but at least it probably more than comes across in the show. A couple more here, and one from Antonia. And it might be for both of you again. Do you have any kind of expectation how long we will likely take to understand dark matter and perhaps even dark energy? Is it years, decades, or centuries?
Tina, I'll let you answer, then I can give you my 2 cents. But
okay, well, I don't know if it's going to be dark matter, but I think we're definitely sitting on the brink of some discovery. So our physics program at the LHC should open up some new window to new physics that's going to answer, hopefully, or go towards answering some of our big questions of the universe that I was talking about earlier. So I hope that we're already starting to see that window open a little bit. We've got some really cool sort of surprising things, anomalies sort of appearing in the data from some of the LHC experiments, and an experiment that was looking at the muon over in the US. And I hope that these kind of anomalies are just going to grow, and that we're going to move to a phase of trying to characterize some new phenomena that we're going to see that is hopefully going to fit in or give us a hint to dark matter. So I hope years for something like dark matter, maybe decades if it takes a little bit longer. Dark energy, I'm going to stay well away from for now.
I have the same. I think so. Really, we start to see some deviations, and we can do that thanks to the precision that we have achieved. So the work that has been done until now to confirm the theory that we know allows us to go beyond the theory that we know. And that's something that it's starting now. And yeah, I think within a couple of years, we will understand whether that deviation is there. And if it's there, that, it opens a completely, new force, that the newspaper were talking about, because that means that there is something that couples to the electrons in a different way with respect to the heavy cousins of the electrons, which are the muons. And that would be very, very exciting, because it tells us that there is a force that we have not discovered yet.
I see we've come to the end of our time. Just very briefly, is there anything either of you would, perhaps following up from the questions, anything either of you would like to say, or what would you like people to take away? What single message would each of you like people to take away from this?
Takeaway that I think from me that some very, very exciting things are happening in particle physics, and I hope that we manage to communicate them to the rest of the world successfully. But certainly do keep an eye open. We've had the Higgs boson. We hope to have some answers for dark matter, or maybe something completely surprising that we haven't thought of yet.
Yeah, and if I may add, I think a talk like this, or what we work on, is fascinating, because it answers questions that, if you want, do not have an immediate application. So are really pure questions that human beings have asked themselves since the beginning of humanity. And it's beautiful to see that it's worth spending your time, the government money, on answering this question, because it's what makes us human, and also because of a lot of beautiful technology that helps people comes out of questions that are completely pure. So I think that's something that for me always fascinates me.
Well, thank you both. I mean, that's absolutely inspiring, and I'm only sorry that Zoom doesn't mean that we can open up to the audience to show their appreciation, but I'm absolutely certain they would if they could. I found it really fascinating listening to you both. But I guess at that point, we will draw a close to the session, and thank for those who tuned in and listened. Thank you very much for that, and I hope you found it rewarding too. Bye, everybody.
Bye-bye.
Thank you, Rachel. Bye-bye.